not too many people have asked questions. So I hope that means we have an understanding of what to do here. But let's just review it because it is really kind of key. So in what was x prime for? Somebody tell me. X prime was what? 0.4 cosine t
minus 0.47 t sine t.
0.t sine t. Okay, like so. And y prime was
0.3 plus 4 cosine 2t.
Plus what?
4 cosine 2t.
Okay, is that right? Okay, so x prime and y prime. Now you were supposed to plug in a 6 into those. And what did we get for x prime? What was the number? Jace, what do you got? 1.0. Okay, and what about y prime, Sam? What do you got for y prime?
3.675.
Okay, now just right there. Okay, Jace, as soon as you type in a 6 and you get 1.055, what's that mean? What's that mean in this situation? What's 1.0? What does that mean?
Times 6, that's slope.
No. Maybe there should have been some questions yesterday. But, what does it mean? Okay, Adam Ant is doing what?
1.055.
Adam Ant is going, it's his horizontal velocity, right? I know that's what it said in the notes, right? What does that mean? It means at 6 whatever seconds, whatever time unit this is, he's going 1.055 inches per second. Where? At times 6. He's going to the right. Okay, he's going to the right because it's positive and it's his horizontal velocity. So we got to understand horizontal means left or right. So 1.055, so what should just be screaming at you when you found that number, right? Sometimes we get too caught up in just the mechanics of it. We plug in the centers, we type it in, vertical bar, however you did it. What's it mean? Okay, it means he's going to the right. And what's 3.675 mean? He's going up. That's his vertical velocity. Since it's positive, he's going up. So what we just found is at 6, he's going up and he's going to the right. Okay? So he's going up and he's going to the right. Now, he's going more up or more to the right? More up. That velocity is more. So more up. Now, if he's going more up than right, in other words, he's going 3.675 times as much up, or 3.675 compared to 1.055 to the right, correct? So now does it make sense when it says what's the slope of his path? That our equation is to take y prime divided by x prime? To take this number divided by this number? Is that what you did on number 3? Right? Use your answers in problem 2 to find the slope of the path. It's just, but if you think about it, isn't that what it's saying? It's saying he's going more up than he is to the right. He's going up by a factor of this compared to a factor of that. And isn't that rise over run? It makes sense then that that's the slope formula for the slope of his path, right? At that instant. So the fact it's y prime over x prime kind of makes sense. But this number, and what'd you get here then? 3.485. And what would the units be on that?
Speed units north over speed units east.
It would be whatever its distance units are north over distance units east, right? He's going 3.485 units north for every unit east, right? So he's going 3.485 times as fast up as he is right. Okay? That's the slope path. But this is not a speed, right? So like Jace went, so when you said that, that's why I was adamant about not slope, right? Because that's where we got to be careful. Because you're right, we're so used to prime is just automatically just slope. But, we got to be careful there. okay? Because derivative is rate and it is slope, that's true, but now all of a sudden we're learning that the units, there's multiple units in this problem, so we gotta be careful, right? As far as which rate are we talking about, all right? If you were gonna just draw a graph of his horizontal position and make it x here and t here, then yes, this would be the slope. X prime would be the slope on that graph, right? But that's not the graph we're looking at here. We're looking at a x versus y graph, his x and his y coordinate. That's different, right? If we just want to look at his horizontal movement, we could draw an x versus t graph. And then this x prime would be a rate, and it would be a slope, and all that stuff, okay? So we really got to take what we've learned, though, and we've got to be specific about it. All right, now, and then this I said I didn't think we could do it. We were just going to calculate that slope. Doesn't matter. Okay, he starts at the origin, goes northeast for a while. When does he turn around and start coming back? What'd you have there?
0.8.
About 0.8. Now what I've done is I went ahead, this is my graph, I went ahead and zoomed way in on that place where he kind of turns around. Okay? All right, now you'll notice here on my T graph here, there it is. Okay, in my graph here, I've got the t-step 0.063. Now, I don't think it would let me, it said to put 0.01. I don't know if you noticed this, it said to put 0.01. Like I zoomed in and I tried to put 0.01 and it wouldn't let me. It kind of adjusted that for me. Okay, now so Harish has this, okay, so about 0.8 it goes up and then it comes back down, okay, but about 0.8 it does that. All right, so back to this. All right, reset the t range to go from 0 to the time out first arrives back at y equals 0. So that's about 1.7. Okay, now I went ahead and zoomed in a little more. Use a t-step 0.1 to get a fairly accurate graph. Because what happens if, remember the t-step is how many seconds or whatever. So if you do a t-step of 1, it's going to plot where he is each second. Well, then that graph could end up looking like, you know, because he was here, then he was here, then he was here. And if you have too big a time interval there, right, you don't get a good graph. So that's why you want like 0.1 or 0.01, and so you get a smoother, more representative graph, okay? And so that I had to play around with that a little bit. You may have had to too. So anyway, he came up, and then he kind of turns around, and then he comes back down, and he kind of loops up, and it comes back down like that. Or I don't know, something similar to that. Okay, but now we get into the more important part right here. 7 and 8 that are really the key to this. And then 8, we kind of look at the graph a little bit. But so go ahead and zoom in if you can. Or actually, I could probably use mine, but zoom in kind of like I did on that part right there. Okay. So now find precisely by calculation the value of t at which y first stops increasing and starts decreasing. So he was coming up, and then he starts coming back down, and like so, right? And so what are you looking for? What do they mean, find by calculation? Well, I hope, what do you do? Is that what equals to? Y prime. That is the key. You got to understand. You needed to take the y prime equation. You should have this written on your paper. Some of you just had an answer that looked like, but you should always write, anytime you're solving an equation on your calculator, you should always write it down. So now we already had y prime written in an earlier problem. So, but that's what we're doing, right? We don't care about x here because it says when the y first, because we can really only deal with one at a time, right? So when does he quit going up and start coming down is what we're asking. Well, that's when y prime is 0 because y is his up and down velocity, okay? So when you solve that, what'd you get?
0.8229.
Okay. You guys get that? Okay. You didn't get that? What'd you have? Pi. Ooh, that's weird because that's 3. Now that could be another time.
That happened if you didn't put a parameter up there.
If you didn't do 0 and 1.7. But didn't you get enough? This should have been 1 up 2 though. You just got 1.
You said pi times.
Oh, you got that. Okay, so whenever, yeah, that's a great question. Thanks for remind me of that parameter thing. Okay, so we're solving. So let's go in, Harish. Let's go in here and let's look at that. So okay, so we got a similar thing here. Now let's go to your calculator screen and do a solve. Okay, so our solve is 0.3, right? Plus, or was it minus? Plus 4 sine cosine 2t equals 0, comma, t. Now, go ahead and hit enter. That's what you're talking about.
Yeah, that's better.
Okay. But when you ever see that N1 in there, that's a problem, right? We can't just ignore that, right? Because what's happening is when we have a cosine or a sine and we do a solve, there's multiple solutions. Where are we supposed to be looking here? Between where? 0, 1.7, roughly, right? When it went up and came back down. So, Harish, go ahead and grab that again. And now we got to put, this is where we put the vertical bar, and then we got to limit it from 0 to 1.7. Did I say that? I thought I meant that. Okay. I might have said that in the other class. Okay, there you go. Okay. So then you got to, so if you would scroll and continue this out, if you put different values in here for N1, like a 1 or a 0 or a 2 or whatever. So I'm guessing as he was zipping around the, thing, there's a lot of times where he quit going up and started going down, right? There are a lot of different times where he quit, his Y prime was 0. He stopped going up, started coming down. A lot of different times. We just wanted this first. Okay. So there it is. Now, does our graph show this? Well, I'll just go to mine real quick. And so if I trace at a t-value of, what did we say it was? 0.8229, and I graph there, sure enough, that looks pretty reasonable. It looks like he is not going up anymore. But it does look like he's doing what? Going what direction? Well, we think. I guess you'd have to move it a little bit. Yeah, okay, so going 8219, 8229, 8239, right? Looks like he's going to the right. So then the next question is he stopped or is he still moving? Now, we just showed graphically, but we need to prove. How could you prove that at that point he's still moving? Do what? So in other words, probably I think the best option is to plug then your 0.8229 in to x prime. Okay, let's think about this now. See, what's hard about these problems is you got so many different equations that you really got to stop and think, what does each equation represent and what am I trying to find? Is he stopped? Since we got two-dimensional motion, if he stopped, his velocity in both of them has to be 0, right? If he stopped, he can't be going up, down, left, or right. So x prime and y prime both have to be 0. Now you could do the same thing you did in 7. You could take x prime, set it equal to 0, and see if you get the same value. See if you get 0.8229. That'd be an option also. But maybe a better option is to just say, well, what is his horizontal motion at this time? Did anybody get a value here? Just plug that into x prime, which was your 0.4 minus 0.4 t, whatever. By the graph, we better get a positive value, because it looked like he was going right.
I got 0.2239.
0.2239. So at this time, is he stopped or still moving? Justify your answer. That's your justification. Your justification is he's still moving because his x prime is positive, not 0. So he's moving horizontally at that instant, but he's not moving up or down. Okay? So if x prime is 0, so what would happen if x prime is 0? So let's say there's a time comes, so he's moving up. Now he's coming back down, and then he goes like this. Well, wouldn't it be about here? Wouldn't it be about there that he would quit going horizontally? Right? Right there he would quit going horizontally. Oh, guess what? What's the slope of the path right there? What's the slope of the path when he quits going horizontal? Undefined. Oh yeah, because x prime is 0. When he stops going up and down, what's the slope of the path? 0. Oh yeah, because y prime is here, right? Now if they're both 0, he would be stopped, right? That is what we were just saying. He would be stopped, and there wouldn't be, that'd be like a sharp point or something, right? And the slope would be undefined as well, okay? But he wouldn't be going one of those two directions, okay, if he stopped. All right. So that is, and then zoom in on the point. That's what we were just looking at. Okay, so zoomed in on the point. So back to this. So that's the kind of question. Something like that would be the kind of question I would be asking about this motion and how you could use. The only thing we didn't ask is what was his speed, right? So we could at some point we could do speed. Well, then you just take the x prime value, the y prime value. T equals 6, right? What we did earlier. T equals 6 was speed. We just take that x prime answer you had, the y prime answer you had, stick it into that equation. Okay. All right. So let's do this problem right here. Kind of work on your own and help each other if you need to is fine too. Okay. But let's just do this. Okay. Here I've given you a parametric equation. I've given you some window settings. You don't have to graph it. Okay, I'm not asking for a graph in this case. Now, we're going to want to be able to graph them, right? We're going to, on the quiz, I may have you sketch a graph, of one. I may have you trace some values. I may have you show direction of travel, like put some little arrows around it, showing which way it's going. So we'll practice that later. That's easy. But let's make sure we can do all these things that we got these equations for. Horizontal velocity, negative 11, 872. I didn't give you any units here, so that's fine. Vertical. Okay, right there, that tells you what's happening. Left and up, right? Left. So first thing you got to be able to do, right, is the mechanics of the calculation. So that's kind of what this problem's about. But then, again, the more important questions and the ones that are tougher, trickier, whatever, would be then ask you about what's going on with that. What's that mean? And so this particle is moving up and to the left. I might just say describe the direction of travel at t equals 2 or something like that. So going up and to the left. And mostly left, right? More left than up, right? By a fair amount. Slope of the path would just be those two. Now, I would say, now, again, if you're doing this work on a quiz, you should have the x prime equation written out and have x prime of 2 equals probably y prime of 2 equals, right? Show what you're plugging into, that kind of thing. Slope of the path, then we're just going to, oops, I got those backwards. 2.881 divided by negative 11.872, right? Like that. That probably should take a few more decimal places than that, just to make sure you get 3 in your answer. What was that? Negative 0.243. Okay? And then the speed was what? 12.217, which again makes sense that it should be more than either one of these, right? It should be bigger because it's Pythagorean theorem, so it's the hypotenuse, if you will, of these two. But also, it's got this much speed just in one direction, and you're adding on some speed in an upward direction as well. And so the number should be bigger than either one of these, and it should always be positive. Okay, all right, so again, we can then use that, but those are the basic calculations we've got to be able to work out, okay? with parametric. So really, at the end of the day, it's not hard, right? I mean, if you memorize those formulas and you get that, it's not that bad. Okay, let's look at some other stuff with parametrics that we can talk about. Probably won't end up doing a lot with these when it comes to the quiz necessarily, but you're going to have some of this on the homework today. So go ahead and everybody get your calculators out, and let's go ahead and grab. This is similar to a problem I did with you yesterday. I showed you just real quickly, but let's go ahead and do this. So you can delete out. Well, you can just turn off the out of math. You can delete it. We're probably done with it. But you can delete it. Oops, wrong screen. We're probably done with it, but now go into your parametric mode and put in these two equations here. X equals t, y equals t squared for one of them, and then x equals t cubed and y equals t to the 6 for the other. Yeah, I think we could leave the range at the default. That's probably fine. The window, well, you can kind of figure it out when you see it, okay? You know, if I don't give you a window, you can kind of figure out, okay, look at the y. The y is always going to be positive because it's squared, right? So you don't really need much on the negative side of the window for y. So your y window could maybe go 0 to 10 or something. Your x window could go negative 5 to 5 or something like that. The t could go 0 to 6.28, just the default. And then we'll look at it and we'll see what we're getting. Okay. Yeah, maybe go, make it a little what? Maybe you could do your y maybe negative 4, your y min negative 4. That's pretty good. So you see a little bit down there. Okay. Now, what do we got? What do we expect that we would have, or what does it look like it is? What's it look like? Looks like the top half or the right half of a parabola, right? Just the right half of a parabola. Now, back to what I was saying yesterday, and we're gonna talk about this. It's called eliminating the parameter. Okay. Now, this is the simplest type you can do. Matter of fact, if you want to take just a regular old function and graph it, the best way and do it as parametric is to do this. Let x equal t. Just let x equal t, because it's a simple substitution. If x is equal to t, then this has got to be the graph of y equals x squared. So it is a parabola, right? So if I wanted to draw the sine graph, but I wanted to do it in parametric mode, I just let x equal t, and I let y equal sine t. And then that is going to be the graph of y equals sine x. It's going to be the sine graph. Now, the nice part about parametrics is we can look at just pieces of the graph very easily, right, as you see here. Why are we only seeing the right half of this parabola?
Because we said the range from 0
Hit tab, yeah, hit your tab. It's not because of the x and y, right? The x went from negative 5 to 5. It's because of this right here. And since x is equal to t, we've essentially only graphed the part where x is from 0 to 6.28. So if he zoomed out even more, we would see that this parabola would not keep going forever. Why don't you do that? Why don't we set our y window to y max to 50. Oh, and we got to set our x max, so we go up to 6.28. So set your x max to 7. So not only do we see the right half of the parabola.
Should I go to like 20?
Oh, I don't want. Go back, tab back to your thing. Tab back. Okay. Arrow up. Go down to Y2. Turn that off. was only the red graph that kept going, the blue graph didn't. Okay, so click that off, hit enter.
I just hit it.
Okay, see how it stops? Okay, so it stops when x is 6.28. So that's that last point. So do a trace and type in 6.28. Okay, so that's where we're at. Okay, now the red one kept going because the red one is different. The red one is x equals t squared, right? So now if t goes out to 6.28, that's actually 36 something. So it's going to go on a lot farther. We got a lot bigger piece of that. But if you still do a substitution, this is going to be y equals, and in place of, well, if you look at t to the 6, isn't that t cubed squared, right? So, and what's another name for t cubed? X. So look what we get. So again, this is that example of these two parametric equations are the same path, but they're describing different motion on the path. So let's talk about the speed. What would be the speed of each of these particles at t equals 2? What would be the speed of each of these particles at t equals 2? Go ahead and calculate it real quick. The speed of both of these at t equals 2. Now go back and turn that up the graph. So both these particles, so let's assume both these particles started off at the starting line at the same time, 0, 0. So at time 0, they're both at 0, 0, right? And actually at time 1, they're both where? Where are they at it when at t equals 1? That's something I guess we never talked about. When I say where are they, what do? You just put a 1 into here, right? Put a 1 in here, 1 in here. That gives it the x coordinate and the y coordinate, right? So you put a 1 in there, that particle's at 1, 1. You put a 1 in here, this particle's at 1, 1. So they're at 0, 0 at the same time, they're at 1, 1 at the same time. Now, how about in between, at half a second, are they going to be at the same place? They're not, right? So at 0, 0 at the same place, at 1, 1 they're at the same place. Kind of interesting. Well, which one's ahead? Let's just do that real quick. So that they're both at 0, 0. So put in a 0.5. Put in a 0.5 into those two equations and give me the coordinates of each of those points at half a second. So this one's at 0, 0 at time 0, and then it's at 1, 1 at time 1. So is this one. But at half a second, where's this one? 0.5, 0.25. So it's went up a quarter. So for half a second, it's went up a quarter. Okay? This over a half and up a quarter. This one at half a second is at 0.125. So at half a second, he's way behind, right? I mean, he's at 0.125, okay, compared to this one. And what's his Y value? 0.0165. Okay, whatever. He's way behind, right? Way behind. After half a second, he's like he's barely moving, right? Yeah, that's kind of like Sam and I in the race. And this, Sam, he's a little slow in blocks. He's a little slow in blocks, but he's going to catch up. I think he's got more endurance in him. It's like soccer running around. Okay, 1-1, right? But now he's catching up. So by 1, he's caught up to it, right? He's caught up to it. Now, what's the speed? Now, what do we got for the speed? What do you get for the speed at 2? I've started it, but then I kind of square root of 17. Does that sound right? So 4 point, what is that? Something. 2 whatever. And how did I do here? Is that about right? 3, right? We're doing x prime, y prime. Take those numbers, square root. What'd you get for a number here?
192.375.
I mean, look at that speed compared to that speed right there at 2 seconds. I mean, the thing's just taking off because where is he? He's way out there. We already said that on the blue graph at 6, with t equals 6.28, the blue graph was there. The red graph was way, way out there. I mean, it's just taking off. And the speed is just way, way more. And his coordinate would be way out there. He'd be, if you put a 2 in there, it's 8. And you put a 2 to the 6, what's 2 to the 6? 64. So at 2 seconds, this one is at 864, whereas this one's at 2.4, right? So, I mean, that one is just taken off. And so they're at very different places, but they're on the same path. The 2 equations are exactly the same. Okay, 2 different particles on the same path. Okay, so let's talk about this right here. All right, so go back to your function mode now. Everybody go into your function mode on your calculator. Go into the function mode on your calculator and graph that equation on the left. Now remember, in function mode, you have to use x's, right? You have to use x's. Okay, so now what I want to do is I want to kind of compare this back to what we had been doing before Christmas. We were talking about particle moving on the x-axis. So this would have been a type of equation we would have seen if we were doing a particle moving on the x-axis. Okay? And so we would have had this right here. Okay, so go back to function mode, type in this. I don't know, maybe we need to turn off or delete those other ones. I don't know if they'll still show up. So you might have to go in and delete those. But let's put this in function mode. Remember, you can't use t's, you have to use x's. And let's set, well, we'll just find a decent window here. (3x cubed minus 4x squared plus 6. And this is what I was talking about earlier. This is going to be horizontal motion, particle on the x-axis. So right would be to the east, right? Negative left would be to the west, and that's why I said miles east. And then let's say this is hours, okay? So maybe this is a car. This is the Bismarck problem. Maybe we talk about that. But it could be just a particle on the x-axis. All those position, velocity, acceleration problems we did before. Okay, so Harish, what do we got? So you got this, okay? So something that looks like that. Now, what's this tell you about the particle? What does this graph tell you about the particle? When is it at Bismarck? When is this particle at the origin on the x-axis? Where would that point be on here? At what time is this particle that's moving on the x-axis back and forth? Bismarck's right in the middle at 0. This is east, this is west. Huh?
That stays.
Right here. Right here. Right here. Right? Remember, what are the units on this? The Y units are miles east of Bismarck. Positive would be east, negative would be west. So right here, the car, if we're doing the Bismarck example, the car is what? To the west, but coming back towards Bismarck, right? And now it just flies right on by Bismarck, right? Let's say 0 is noon. So this would be at 11 a.m., -1, right? Now it flies right on by Bismarck. Now it's east of Bismarck, right? Now what's it doing? Still east of Bismarck. Now what's happening? It's now 1, 2, 3, 4, 5, 6 miles east of Bismarck, right? It's now 6 miles east of Bismarck, right? You put a 0 in for X, what do you get? A 6. Yeah, okay, that's its miles east. It's east of Bismarck. Now what's it doing? Back towards Bismarck. Changes his mind. Turns around. Now going away, right? This is position, velocity, acceleration, right? How many times did it stop? Once there, where the slope is 0, right? Turned around. This is increasing, decreasing, increasing. It's positive slope, negative slope, positive slope, right? That's what the number was, right? Okay, see it? We got it. You know, we'd been good if we just would have shouted that out, but now we're throwing in this other stuff, and so you got to think about it. Okay, but that's what we were doing before. That's what a time, remember, X here's the time. So time versus miles east, okay? So that's what that graph would represent. So it came up here, it went like this, it came down, right? That's good. Okay, something like that. Okay, now where was that? Did that happen right at 1, I think? I think it probably did. I think that happened right at 1. So it turned around at 0 and then at 1. Okay, now let's go to parametric mode. And again, did you turn off the parametric ones? Yeah. Were they showing up if you don't? Okay, now turn this one off. And now let's go back into parametric mode and let's delete out those other ones. And now let's do this. Now let's do this one over here. Now let's actually plot the actual movement of this car. So now, since it's only moving horizontally, doesn't make sense that the y equation of it would be 0. If the particle's always on the x-axis, then its y-coordinate is always 0. So we can use parametric equation to describe the same thing. But understand, our graph is different now. Our graph has x along the bottom, which is its miles east, and y along here. Okay? But what's y always going to be? Y is always going to be what? 0. So this is just going to actually be a graph. Now, I don't know if we're going to be able to see it. Our old calculators used to do this a lot better. Okay, what are you doing? You graph it?
Yeah, but it just should be the same.
Well, you got to delete. You got to turn off that.
Oh.
Go turn off that. You got to go back to function. Yeah. Now we're going to have to set our t from about. Let's set our t from let's say -3 to 3.
To get rid of it, do I just
No, you gotta go back into your menu. I think you gotta go back into graph entry function,
oh, and then I just
and then turn it off and just delete it, whatever. You do it. Okay, hit it. All right. Now it's hard. It's hard to see this, but we got to trace. So we're going to have to trace. But do you see how the graph's just right on the x-axis? Well, that's what it should be. That's the beauty of parametric. That's Adam Ant, right? The Adam Ant. What was cool about the Adam Ant graph is that was his literal motion. That was his literal path that he was traveling. See, when we had this function graph up here, that wasn't the path of the car. That was a graph of its position over time. What's cool about parametrics is it actually graphs the motion. It actually graphs the path. So this is a particle moving on the x-axis. So now type 0 in. Or no, let's type -3. So this would be 9 in the morning and 0 is noon. So type in -3. Here's the particle. He's way out here where? West of Bismarck. Now, hit right arrow. Hit right arrow. Okay? So hit right arrow. Where's he coming? Here he comes. Keep going. Keep going. He's coming. He's moving east, right? He's headed towards Bismarck. Like we said, now when do you get to Bismarck? Keep going. At 11, right? We're at 10 a.m. now. Okay, here we come. Here we come. We're getting closer. We're getting closer. Look at this. Here it is. Boom. Whoops. Went past it. Now he's kind of slowing down. Do you notice this is going in 0.1 increments? Go left a couple more. Go left a little bit. Look at this. Okay? Okay, go right. Now maybe not too much. Maybe not slowing down too much, but here we go. But he is slowing down a little bit. It's past the inflection point, so it's slowing down. Okay, there he is. Oops. Wait a minute. Oh, it must not have been right at -1. That other graph wasn't crossing right at -1, right? We said it was crossing right there at 11 and -1. It wasn't. It was really close. I think. It was. Okay, keep going. It's somewhere right in between -1 and right arrow between -1 and -0.9. So that right. So we were saying it was -1. But so that now he's past Bismarck. He's going. Now it looked like keep going. Okay. And when did he turn around? Keep going. Right arrow. Looked like at t equals 0. Remember, we said he was 6. He got the 6 miles east of Bismarck. He got the 6 miles east of Bismarck. Now right arrow again. And now look, now where's it going? It's going back to the left, see? So right arrow, it's going back to the left, right? It got 6 miles east. Now right arrow, then at 1, it looked like it turned around, didn't it? And now he's coming back to the west. Right arrow. Now it's just going to go out and keep going forever. See that though? So that's literally, now our old calculators, I really liked our old calculators. They had a mode where we could put a dot here and we could go really slow and we could slow it down and it would actually graph and you could just see it. You know, you could see it come and slow down and then go back and then go, right? Here the only way you see it is to actually trace it. Okay? So that's what's great about it. So all those problems before Christmas where we're talking about particle motion and a particle moving on the x-axis, parametric equations lets us actually graph that motion, see that path, and see it happen. Okay, so just understand the connection here between those two things. Okay, so here our graph was, it came in and and it went like this, and then it turned around, and then it turned around again, and then it went back. Right, that's what we were talking about. But we see the connection between those, but the equations are essentially the same. Right? We just say, we want particle on the x-axis, just like the y b 0. And it'll stay on the x-axis. Okay, last thing, and then we'll have a little work time. So the last thing we want to be able to do, no, not last thing, 2 quick things. These are quick. Eliminate the parameter. So the easiest ones to eliminate the parameter when you have a simple substitution you can make. Okay, so if you have this parametric equation right there, well, that's easy. You just substitute and you let y is equal to e to the x, right? X is equal to t, you just substitute. So that's the easiest one of all. Now, one that's pretty easy is one like this, where you could just say, okay, x equals t cubed. Well, that would be t cubed squared. We can just make a simple substitution, right? Sometimes we got to go a little farther than that, and we actually can solve. As if you don't have, like these are both linear, okay? So what we would do so if you want to jot this down, because you're going to have some of these. These are actual line segments, right? Because what you're going to have, just like we said, you get a part of a parabola, depending on what you set for your window, and they'll tell you what to use for the window. Like they might say, okay, do this from the time 0 to 2. So you put a 0 in for t, put a 2 in for t, and basically it's going to be a line segment. Anytime both of these are linear, it's going to be a line. Okay, but what we can do is we can solve this top one for t. And so we get -1/3 x plus 2/3, right? If I just divide by -3. And then I could substitute that back in. So I get y equals 4 -1/3 x plus 2/3 minus 1, which would be y equals -4/3 x plus 8/3 minus 1, which is y equals -4/3 x. 8/3 minus 3/3 would be 5/3. Okay, so what you will get if you were to graph that parametric pair up there, you would get this line, okay? But then it would just be a piece of that line depending on what you set for your t values. Okay, so it'd be a line segment. You'd get a segment of this line right here. Okay, but eliminating the parameter is saying, okay, take this equation. Sometimes you just can't do it. Sometimes it's just not an easy thing to do. You can't do it. But for just basic graphs, we can do it. Okay, so eliminating the parameter is saying, okay, you got this x and y equation in terms of t. T's the parameter. We're getting the t out of there and turning it into a regular y equals x kind of equation. Okay, and again, what that is going to be, though, is the path. The downside to the y and x equation that we're so used to is all that gives you is the equation of the path, not the actual movement at a certain time or the values at a certain time. So the parametric equations give us a lot of information because we know where it is at certain times. Okay, this just tells us the path. Okay, is all. But sometimes that's good to know. Okay, sometimes that's good to know. So you'll have some of those. All right, here's the other thing. Inverse functions. When you first learned last year about inverse functions, or maybe in Algebra 2, one of the things we've talked about is to do an inverse function, you interchange what? You interchange the x and the y. Well, think about a parametric. You have a separate equation for x and y. So we know that this graph right here is what? What graph is this going to make? What is it? It's just your basic y equals x squared parabola, right? We were just working with that. We know that's y equals x squared. Now let's take and interchange the x and y, which means let x equal t squared and let y equal t. Graph that. Go into the parametric. Delete whatever graph you have in there now. Go into parametric mode and do that. Just interchange the x and the y. Interchange the x and the y. So just put t squared there and put t down there and hit enter. Right? And the cool thing about that is you get the whole thing, right? You get both. It's not a function, but it's the inverse of x squared. We get the actual sideways parabola. And it's a neat, quick way. So if you want to get the inverse sine graph, right? You want to get the inverse sine graph, the arc sine graph. Well, a normal version of the sine graph would be this. Oops, t. So now just interchange those. Let x equal sine t, and let y equal t. And that is going to be the inverse sine graph. And it'll just be the sine graph wrapped around the y-axis, which is what the arc sine graph is. Okay? So it's a neat way to do that. And here's the other thing. But now you say, well, why is that a big deal? Because I could do that anyway. I could just interchange, get x equals y squared, and then solve for y. Y equals plus or minus square root of x. Sure, that's true. You could do that. But what about one like this? Interchange the x and the y. Right? X, so go into your parametric and do this. So you get, this is the graph we just had up there a minute ago. Went up, came down, did that, right? You interchange the x and the y. There is no earthly way you can solve that for y. There's no way you can solve that for y. So how do you graph that? Well, you do parametrics. Okay? So we're just going to flip this around. So we're going to, oops, you need to see. So put x equals 3t cubed. So we want x equals 3t cubed minus 2t squared plus 1. Now this is a little more just kind of for fun and kind of for some information. It's not probably going to be our next quiz. This maybe inverse. They might have a little bit of inverse in the whole where they want you to maybe interchange and put in something. But now look at his graph. Okay, and we got the inverse of that one we just had. Okay. So parametric equations can be useful for various things. You go into Calc 2, you'll do more with parametric equations. Farther into Calc 2, we're getting into a little bit of it right now, but there's more of it in Calc 2. Okay. All right. So one of the things I mentioned just a minute ago, so I just want to show you this, is we talked about marking the direction of travel. So, and looking at some dots. And so they're going to give you some problems with the parametric and have some dots. And so you graph this, put some arrows, this is the direction of travel. Also, the farther apart the dots are, what's that tell you? The faster it's going, so it tells you something about the speed. Also, they're going to have you do some estimates of how far it's traveled, like from here to here. Well, like from here to here, it's almost horizontal, so you can probably just look at the graph and see about how far it's went. From here to here, it's probably more of a, kind of a, maybe a Pythagorean theorem kind of thing. How far, it's almost straight, so how far did it go in that time period would be how fast, where you could kind of do a little Pythagorean, so you can do some estimating. So they talk about that. Okay, the last thing, you're going to have a problem on your homework. That talks about a baseball pitcher throwing it, and this is where we could use parametric equations to describe the path of the ball, and so we could do a somewhat interesting problem to answer the question: is it a strike? How fast is the ball going? All these kind of things. Okay. Now we're going to do something here in the beginning of this problem. I'm going to go ahead and help you get started because you're going to have a homework problem similar. And that is, all we're going to say is, number one, we're going to say that he's releasing it, I think they say from a height of 7 feet, because you got the mound and everything else. So I think they say that he's going to release it from a height of 7 feet. And when he releases it, he's going to release it with a horizontal velocity of 150 feet per second. Horizontal. Okay, and then gravity's going to take it down. Now, gravity's the only thing we're going to think about here. We're not going to apply wind resistance, which is kind of silly, because without wind resistance, the ball won't move very much, right? Pitcher loves wind resistance, right? Because that's how they curve it and make it move. But for right now, we'll just say it's gravity, okay? So he's going to release it with 150 feet per second. So what velocity would that be? In our parametric language, what would this 150 represent? What label could I put on this 150 instead of b sub 0? Not x. X prime. It's rate. This is a horizontal velocity, right? This is a horizontal velocity. So I have x prime is 150. Okay? Well, what would x be then? 150 t plus some c value. So now I need to know an initial condition. Well, at time 0, we're going to make the home plate be a distance of, no, let's let this be 0 back here. This is going to be 0 back here. This is going to be 60.5 right here. 60 feet 6 inches, right, from home plate. So at time 0, what's x represent? If this is horizontal velocity, what's x? Horizontal position. So at time 0, what's its horizontal position? 0, right? Right here, 0. So what's c? 0. Okay? So there's my x equation. Now let's talk about y real quick. What's y prime start out as? When he releases the ball. Ooh, it's 0. Well, that didn't help us much, right? That didn't help us much. Oh, you know what we do know? We know, I heard you say it, 9.8, right? Gravity. Isn't that y double prime? Isn't that the acceleration in this direction? And it would actually be negative, right? Now this is feet though, so we're going to use negative 32. Okay, 32 feet per second per second. So if that's true, what's y prime? Negative 32 t plus c. Now y prime is what? What's y prime represent? We're getting better. Vertical velocity. Vertical velocity, right? What's its vertical velocity at 0 when it's released? It's 0, right? It's only going horizontally when he releases it. So at time 0, this is 0. So we know that c is 0, right? So sure enough, at time 0, the velocity is 0. So what's y then? Negative 16 t squared plus some c. Now, what is, at time 0, what is y? 7. That was that number. So we know that's going to be a 7. So C's got to be a 7. So look what I just built. So based on just knowing some simple physics, I just built this parametric situation for the path of the ball. Right? The path of the ball is going to be this. Now you could calculate, you could plot that on your calculator. We could do our x prime, y prime. We could see how fast the ball. So let's just talk through this real quick. Okay? So I asked you, when does a ball cross home plate? Now I don't even want you to write this down because I want you to have to think about it again later. When does the ball cross home plate? When x, see, because you got all this stuff now. You got t, you got x prime, you got y prime. You got to know what each one of them stands for. When does the ball cross home plate? When x is 60.5. So can't we go to this right here and put a 60.5 right there? We know when the ball crossed home plate. Now that we know when the ball crossed home plate, how fast was it going when it crossed home plate? What do you need? You need this, right? You need this. What t are you going to use? That t we just found when it crossed home plate, right? X prime, y prime, you're going to have to find those. You're going to use that time, put it in there. That's how fast it was going. Was it a strike? Now, we're not going to know this direction, right? We're throwing it, and we're just going up and down here and this way. We're not going to go side to side, so we'll assume it was coming straight in, right? Was it a strike? What do you need to know if it's a strike? How high it is. Did he swing? No swing. He just up it. No, not even. What? Is it a strike? What do you need? What value do you need to find? You need to find y. You need to find that. So you need a t. What t are you going to plug in? T you found before. See what I mean? We can answer all kinds of questions about this scenario that would be pertinent questions, all based on these different equations we have and the values we found. So, okay, now in the quiz, I'm not going to make you come up with your own equation here with this. It's not that hard. Just need a couple pieces of information. But we've got it, okay? So I think there's a homework problem to ask you something like that. Okay, so on your assignment sheet, I think it's 4.4, day 2 or something, whatever the second line. Second line there is. Or not, yeah, 4. Just the, yeah, 4.4, 1, 3, 5, 6, ABC, 9, 11, blah, 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 that stuff. Okay? So the 4.4 line. What's it say here? Number 12 in class. What is that? So it's pages 248 to 250. Yeah, don't worry about 12. Don't even worry about 11. Let's skip 11 and 12. Okay? Skip 11 and 12. Yes. Yes.
Is there three-dimensional pyramid?
Yes. And that's all I know about. Calc 3, it was funny, I was just talking to Emma Rody, some of you guys, Emma Rody probably. She's in Auburn. She actually took Calc her junior year, and then she took Calc 2 down at UK last year. And she's in Calc 3 right now. And she said, that's funny, she was actually giving a compliment, which was nice of her. But she said she's got a foreign teacher, professor for Calc 3, and they're having a lot, her students, her fellow students, they're having a lot of trouble understanding it. Which was interesting. I had a grad student, when I took Calc 3 in college, I had a grad student teaching it as well, and we couldn't, matter of fact, it was so bad, his English was so bad, that the first day when he took attendance, people could not even understand their own name being said. So he would read a name, and everybody'd look around, and he'd read it again, and everybody'd look around, And then he'd go up to the board and he'd write it out, and then somebody go, oh, yeah, that's me. You know, yeah, which is all. So pretty soon he just started writing everybody's name on the board. I mean, so makes it tough, you know, tough enough without understanding what's being said. So anyway, she was saying that, but she said, well, you know, she said, I just remember what I learned in your class, because it's basically calc 1 in 3 dimensions. You know what I mean? That's kind of what calc 3 is. I mean, you go into 3 dimensions and you start doing derivatives and integrals like we'll do and stuff like that. So yes, that's when you can see that again. All right, I don't know why I just put that up. It's gravity. So the acceleration of gravity is negative 9.8 meters per second squared, or negative 32 feet per second squared. So it's gravity.
And then